it seems like you don't like Nearpod, so I'm not doing that. Okay. So.
It just slows everything down.
Yeah, it does. It does slow it down. So, all right. So this is section 3.1, exponential functions, and this is the definition of an exponential function. An exponential function f with base b is defined by f of x equals b to the x, or y equals b to the x. So this is function notation, this is letting that be y. Now, so these mean the same thing, but anyway, in order to be an exponential function, the variable has to be in the exponent. Okay, and so for instance, f of x equals x squared is not an exponential function. Okay, the variable has to be in the exponent. So this is in the exponent, b to the x. And b is the base. So when we have exponents, we have a base, and then we have the exponent. The x is the exponent here. The x doesn't have to be the whole exponent. It could be b to the x plus 1. It's fine, it's still exponential. So that's the difference between, so this was a quadratic function, polynomial function, not an exponential. So we had to have our variable in the exponent for it to be an exponential function. Okay, so here's an example of an exponential function. The exponential function, f of x equals 42.2 times 1.56 to the x. It models the average amount spent in dollars at a shopping mall after X hours. So what is the average amount spent to the nearest dollar after 3 hours at the shopping mall? So our X is 3 hours. And so we're looking for f of 3. And that's 42.2 times 1.56 raised to the x power. Oh, we got to replace that with 3, right? 3. We had to put a 3 in there because we're doing f of 3. We replace x with 3. Okay, so we're going to bring our calculator up. We're going to do this on a calculator. And I reminded my class this morning, you guys have a favorite Aunt Sally, you know, who helps you with order of operations. Please excuse my dear Aunt Sally. So obviously you do exponents first, and then you actually do multiplication, division, left to right. If division's to the left of multiplication, you'll do it first. But anyway, do the exponent first. So I showed this to the class this morning. Is if you type in 42.2 times parentheses 1.56 and only raise the 1.56 to the third power, and you get, and they want the nearest dollar, so we get about $160. This is in dollars. That's our answer. Okay, so I showed the class, if you do it like this, it's wrong. So you hit enter, and then you take the whole thing to the third power, that's wrong. And you know that the shopping malls would love it if you spent $285,000 in their stores after spending 3 hours at the shopping mall. They wish this equation went like that, but no, that is not a correct answer. So be careful with your order of operation. Okay, graphing. We're going to graph an exponential. So while we're graphing, we're going to review some rules of exponents. You need to know your rules of exponents, so we'll review them. So we're going to just make a table of values and pick convenient values of x. Like we're going to pick -3, -2, -1, 0, 1, 2, and 3. Okay, I'm just picking. They're right here. They're going to be convenient values of x. So, y equals 2 to the x, when we put in -3, we get 2 to the -3. So I'm going to write up here, what does it mean if you have an x to a negative exponent, say -a? That means you make a fraction out of it and you put the base, x, and make the exponent positive and you put it in the denominator. That's what that means. And yeah, if you had 1 over x to the minus m, you would write that, you move it up to the numerator, then you wouldn't need it to be over 1. So that's some rules of negative exponents that you may have forgotten. Just a reminder, they're also posted in my P2L under content under prerequisite material, David Haga notes from years ago. So, okay, so this is 1 over 2 to the third, and that's 1 over 2 times 2 times 2 is 1/8. 2 to the third is 8. And that's approximately 0.1, or that is as a decimal. I'm just going to write it as a decimal. It's 0.125. All right, the next one, 2 to the -2 is 1 over 2 squared is 1/4 is 0.25. And 2 to the -1 is 1 over 2 is 0.5. And 2 to the 0, anything raised to the 0 power is what? 1. So it's a 1. And 2 to the first power is what? 2. Anything raised to the first power is itself. And of course 2 squared is 2 times 2, 4. And 2 to the third power is 8. 2 times 2 times 2. So there it is. Got my points. We're going to graph that. -3, and we're pretty close to the x-axis. -2, and that's a quarter. -1, and that's at a half. 0, 1, 1, 2, 2, 4, 3, 8. No, that's 9. Easy to do. Okay. Okay. And then you connect that with a smooth curve. And put arrows on the ends. And this is a horizontal asymptote. Now you can't use the rules for finding horizontal asymptotes that we used for rational functions, because this is not a rational function. So you're going to just have to memorize that, unless I give you take home. that the asymptote of y equals b to the x is at a horizontal asymptote at y equals 0. Okay, so the base here was 2. Our base, which is our b, was 2. And so this is typical for when we have a base greater than 1. This is what the graph's going to look like. It's going to go up quicker if it's, it'll go up quicker if the number's bigger and slower if the number's smaller. But it'll look like this. So looking at this graph, when the base is greater than 1, if you project the graph to the x-axis, what's the domain? It's a set of all real numbers. Then we want to write that in interval notation. Minus infinity to infinity. The range. Can this function ever equal 0? And so I showed the class this morning that even if you pick, say, x equals minus 100, you're going to get y equals 1 over 2 to the 100th power. And you put that in your calculator, and it's not going to be 0, but it's going to be very, very small. So you can put in 2 to the parentheses negative 100. And you get 8 times 10 to the minus 31. That's pretty small. That's scientific notation. We got to have 30 zeros and then an 8. Point and then 30 zeros and then an 8. So that's pretty darn small, but it's always divided by 2 to the something, and 2 to the something will never make that 0. So that can never be 0. That's why this is the horizontal asymptote. But so you project, now we're talking about the range, you project it to the graph to the y-axis, so it can never equal 0. It just gets closer and closer and closer until you can't tell it apart from 0, but it's never equal to 0. So the range is a set of all positive numbers. And so that's 0 to infinity. There are no x-intercepts. The y-intercept is always, so how would you find the y-intercept? To find the y-intercept, put it up here. You set x equal to 0, so y equals b to the 0 is 1. So the y-intercept is always 0, 1. You don't have to show me that work if I ask for the y-intercept. For this function, it's always going to be 0, 1. The x-axis is a horizontal asymptote as x goes to negative infinity. F is an increasing function and is 1 to 1. What does 1 to 1 mean? It means it has an inverse. And so we can check that. We check that with the horizontal line test. Okay, so remember, an increasing function, you look at the function from left to right always. If it's rising the whole time. So it's an increasing function, its whole domain. And it's 1 to 1, meaning if we try to draw a horizontal line, we never go through more than one point. Okay, so we're kind of reviewing some of the things we went over last, in the previous chapters, but just with exponentials now. The graph contains the points 0, 1, because that's the y-intercept, 1, b, and -1, 1 over b. So if you want to see why it contains 1b and -1b, put in 1 for x, if x is 1, you have y equals b to the 1, and that's just b. So that's why we get 1b. We can let x equal -1, so y equals b to the -1 is 1 over b, the reciprocal. Okay, so that's why these 3 points are always on that function. And the graph is smooth and continuous with no corners and gaps. So that's how you graph that function. All right, does that even make sense? Have you seen these functions before? Like exponentials? No? Okay. All right. All right, so that's when b is greater than 1. We're going to graph an exponential when b is between 0 and 1. This is the other case. B can be greater than 1 or between 0 and 1. And when it's, so this is an example. We're going to pick our xy, make an xy table. We're going to pick convenient values of x. So, I stapled it in the wrong order. All right. So we're going to pick convenient values of x like -3, -2, -1, 0, 1, 2, and then 0. Okay, so you're going to put in -3 for x, so you're going to take 1/2 to the -3 power. So we do have to review our rules of exponents. If you have a over b, say to the -2, you can, what that means on a fraction is you can apply the exponent to each part of the fraction where it is. And then because they're both negative exponents, you're going to be moving them to the other part of the fraction and making it positive. Negative exponents mean you move to the other part of the fraction and make it positive. And so that would be b over a squared. So a shortcut, and I'll do it over here then, is if you have a negative exponent of a fraction, you could make the exponent positive and take the reciprocal of what's inside. Flip what's inside. So, any questions on that? You remember this stuff? Exponents? So that is, I'm just going to write this as 2 over 1 to the 3rd power, and of course 1 to the 3rd power is 1, so it's 2 to the 3rd, which is 8. And then 1/2 to the -2 is 2 squared. And 1/2 to the -1 means we're going to just flip it and make it 2 to the 1, 2. 1/2 raised to the 0 power, anything raised to the 0 power is 1. So that's 1. And 1/2 raised to the first power is just 1. Let's write it as 0.5 for the graph. And then 1/2 raised to the second power is going to be 1 squared over 2 squared is 1 divided by 4, 0.25. Okay, and so we're going to graph that. So -3, 8, -2, 4, -1, 2, 0, 1, 1, and 1 point, comma 0.5, 2, 1/4, and it goes like this. Draw a smooth line. Has arrows on the ends. It has a horizontal asymptote at y equals 0. If you don't have room, you could mark the asymptote over here, but it's nicer to mark it on the side where it's actually being an asymptote. Okay, so if you look at this graph, this is typical of graphs where the base is between 0 and 1. Here the base was 1/2. So the domain is still the set of all real numbers, minus infinity to infinity. The range is still the set of all positive numbers. Again, no matter what you put in here, if you put in -100, you're going to get that 8 times negative 10 to the negative 31. You're still going to not get 0. So there's positive numbers. The range is 0 to infinity. There are no x-intercepts. The y-intercept is still 0, 1. The x-axis is still a horizontal asymptote, but this time it's as x goes to positive infinity. Just put infinity. F is if you look at the graph from left to right, it's falling the whole time, so it's a decreasing function. And it's 1 to 1, meaning it has an inverse. In the next sections, we talk about the inverse. The graph contains the points, is the same as the previous page. 0, 1, 1b, and -1, comma, the reciprocal. And the graph is smooth and continuous with no corners and gaps. So that's the exponential function. You should be able to graph one, graph it nicely. So the only difference between when b is between 0 and 1 and greater than 1, here's the, everything was the same except the x-axis is horizontal as x goes to minus infinity here and positive infinity here, and it's increasing if b is greater than 1, decreasing, but the rest of it's all the same. So you do have to memorize that it has a horizontal asymptote, and you want to write that it's at y equals 0. You want to write the equation of the line instead of the x-axis. The equation of the line of the x-axis is y equals 0. Okay, so that's how you graph it, and then we can do transformations just like we did with the other types of functions. So this is it. And the most important ones will be the first two here. And these are not as important. And reflection, I doubt I'm going to ask you that, but So the next examples we're using here. I don't know if Math Lab asked you that or not. Let me know. Okay, so look at this. So if you've got, remember these are exponential functions. So if you're adding c, and c is a positive constant. So if you're adding c and you're not up in the exponent, that's on the outside of the function. And if it's on the outside, it changes y, and it changes it in the direction you would think. If you add a positive c, it shifts it up c units. If you subtract c, it shifts it down c units. Okay, what about the next one? Notice you got to be careful on reading these things and writing them too. X plus c is in the exponent, so the plus c is on the inside. It changes x. And it changes it in the opposite way you would think. If you add a positive c up in the exponent, it shifts the graph left c units. It's the opposite way. This has been true the whole time here. If you subtract c up in the exponent, it shifts it right c units. It's the opposite way you would expect. And then reflection, a minus sign in front of the function is on the outside. It changes y, but that reflects about the x-axis. And if you got a minus sign up in the exponent, that's on the inside. It changes x, but that's a reflection about the y-axis. Okay. So we're going to do some transformations. So we're going to use the graph of f of x equals 3 to the x to obtain the graph of g of x equals 3 to the x minus 1. So we're going to show you this. So again, we're going to graph 3 to the x. If you're doing this in Math Lab, you should pick the 3 points. The 3 points it has are 0, 1, 1b, and negative 1, 1 over b. So, but I'm going to write them in order. Minus 1, 1 over b, 0, 1, and 1b. And b here is 3. So this is minus 1, 1/3, still 0, 1, and this is 1, 3. So we can just graph y equals 3 to the x using these 3 points. And I like to make it a little more accurate, so I go ahead and put in some more points. But 0, 1, minus 1 1/3, 1, 3. So what would 2 be? 3 squared is 9. So I put that one in because I liked it. And then this is a horizontal asymptote at y equals 0. So this is the graph y equals 3 to the x. And so you do need to label your horizontal asymptote on the graph. So now let's do the graph of this. We're going to use this graph to make this one. So we're subtracting 1 and it's up in the exponent, so that's on the inside. Changes x. So it's to shift right 1 unit, or we can add 1 to each x coordinate. Okay, so there's our coordinates. So we add 1 to -1, we're going to get 0, and y stays the same. That's a point on this new graph. Add 1 to 0, you get 1, and y stays the same. Add 1 to 1 here, you get 2, y stays the same. So, oh, and what happens with the horizontal asymptote? You need to start with your horizontal asymptote, really. You could make these. What happens if you shift right 1 and it's a horizontal asymptote? Is that going to affect the asymptote? No. The asymptote is horizontal, so when you shift right 1, it stays in the same place. If you shift up and down, then it moves. Remember, we don't have any vertical asymptotes. If you shift right 1, your vertical asymptotes would move, but we don't have any. The exponentials don't have vertical asymptotes. Okay, so we have our HA at y equals 0 still. And then we're going to graph these. 0 1/3, 1 1, 2 3, and 3 will be up at 9. I like to do that one too. So that's the graph of g of x equals 3 to the x minus 1. Okay, so now I'm going to show you your homework in Shelby for a minute. Let's do next time. As long as you know how to do it, it shouldn't take long at all. Here it is. Okay, and I'm mentioning that you can use your calculator. I'll show you how to do that with an example here in a minute. But here's the thing. You're going to be graphing f of x equals 1/3 to the x. And label your asymptotes. Oh, there's only one. Okay, so if you print this from D2L, I don't think this is on the. I think the D2L doesn't have this. But I've told you in class you're supposed to label your asymptote. So, okay, so here's an example. Here's something that you're going to be doing. It's just, here's the directions, but this is what you're doing. And the way to do these is to graph f of x equals 2 to the x first, and then do the shifting to get these. So let me show you. So we're asking for domain and range. So let me fill in the domain on this, and the range, and the vertical asymptote, and the horizontal asymptote, and the x-intercept, and the y-intercept. And I'm going to fill these in. Let me go back to my notes. So just showing you, and there is a second page. But so on this graph that we just did, we can project to the x-axis. So what's the domain? We're going up at an angle, but we're still going up at an angle, so it's going to keep going. So the domain is minus infinity to infinity. The range, project to the y-axis. Remember, it can never equal zero, y equals 0, so the range is 0 to infinity on this graph. What's the vertical asymptote? None. You have to write none. Don't leave it blank. Horizontal asymptote is y equals 0. The x-intercept, none. The y-intercept, that's 0, a third. Oh, I wrote the wrong thing in the last class. I said it was 0.5. Whoops. Oh well. Nobody caught it. Okay. All right. I just had to look back at it. It's right there. It's 0 a third, and that's so. If that's so, I don't ask you to draw the graphs for me, but that's the way to do these problems. Then you can pick out the domain range, and all these exponents will never have a verb. These exponential functions will not have a vertical asymptote. They just have a horizontal asymptote. If you shift down, however, it will have an x-intercept. But okay, and a y-intercept, they'll always go through y. All right, we'll do another example. Any questions on that? That's to help you on this problem. Okay, now we're going to do f of x equals 2 to the x again. We already graphed this once, right? So the key points, I'm going to just write them down. Minus 1, 1/2. So the base is 2. 0, 1, and 1, 2. So minus 1, half, 0, 1, 1, 2. If you put in 2, 2 squared is 4. If you put in 3, 2 to the third is 8. So we already graphed this. This is y equals 2 to the x. And it has a horizontal asymptote, y equals 0, at y equals 0. Okay, now we're going to shift that. Well, we're adding 1 on the outside. That changes y. And remember, that means you add 1 unit to each y coordinate. Oh, okay. So I started with minus 1/2, so this is going to be, x stays the same. So I'm going to add 1 to the half, that's 1.5 or 3/2. That's 2, and that's 3. Okay, when I shift up 1, to shift up 1, what happens to my horizontal asymptote? It shifts 1 up. So our horizontal asymptote, we just add 1 to this, is at y equals 1. HA at y equals 1. So we do want to shift, we want to draw that asymptote. Now we're going to mark these points, and they're going to make sense with the asymptote where it is. Minus 1, 1.5, 0, 2, 1, 3, 2 is is going to be 4 plus 1 is 5. Or you're going to add 1 to each of these. 9. That 3 will be at 9. Or you can put it in. Okay, so there's the graph of x plus 1. It's plus 1. You're out of room. Not up in the exponent. That's why it's on the outside. Okay, so we can find the things that I listed up there again for this. Now I left room for it. So domain, range, vertical asymptote, horizontal asymptote, x-intercept, and y-intercept. Okay, so the domain projected to the x-axis, it's all real numbers minus infinity to infinity. Range, projected to the y-axis, it's going to be 1 to infinity. Always put the smaller number on the left. Okay? Vertical asymptote, none. Horizontal asymptote, y equals 1. Don't just write 1 down, because that could be x equals y equals. You don't get all your points for that. X-intercepts, there's none. And y-intercept is at 0, 2. Of course, I want ordered pairs, so that's what all those directions said. All right, so it's your x-intercept will not always be none if you're shifting down. So I'm going to show on the calculator another example. How to find your x-intercept if you're shifting down. We're going to graph y equals 2 to the x minus 7. And here it is going down 6, 7. So it has its horizontal asymptote shifted down at y equals negative 7. The function is going to look like this. You know, it's going to be here. Just a crude picture. It's going to look like that. It will have an x-intercept. So you're going to find that with your calculator, and I'm going to show you how to do that right now. You're going to put y1 equals 2 caret x minus 7. Since I don't have parentheses around it, the minus 7 is down here. Don't put the parentheses around that. And then you're going to press, and I'll do it in a minute, second, trace, and this is called a 0, so you're going to choose number 2, a 0. And then left bound, right bound, so let's do that. On, clear, y equals, ooh, that looks weird. Okay, so the previous teacher put the calculator in a different mode, polar mode, so I have to go into mode, or I could just clear it out and put it in function mode. Let's see, y equals, there we go. Aha. Or I could have hit reset the calculator. Anyway, it said r equals, that was weird. I need to know how to do that. Wow. Okay, I didn't know you could do that. Okay, so y1 equals 2 caret x minus sign, not a negative sign, 7. And when we leave leave the parentheses off. This is not in the exponent. The exponent is just x. I think the new calculators will display it a little better, do they?
Mine puts it up there as an exponent.
Oh, okay. Yeah, that's easier for you to see.
Yeah.
Mine doesn't. So, all right. So then you do second trace. Trace is up here. All your graphing stuff is up here. And your x-intercept is called a 0. So you choose number 2 and hit enter. Oh, and it's standard. Zoom standard is what you want. It's already in that for me, so I didn't need to hit it. If your window's wrong, you can just choose Zoom 6. Which, okay, so we see that there's an x-intercept here. So we can, oh, I need to do it again. Second trace 0. And now we have a blinking cursor. We just need to be on the left of the 0. I'll move a little closer to it, but it doesn't matter. I'm to the left of the 0. I hit enter. Now it asks for a right bound. So I move above and to the right. Sometimes it's below and to the right, but on this it's above. And hit enter. And then, do I want to guess that it's a 3? You can hit that, I guess. But you can just hit enter also. And it looked like it was 3, but it's not. It's 2.8. So the x-intercept is approximately 2.80. And that's how you're going to find the x-intercept on one of those homework problems. So this has been recorded, so if you forget how to do it on your calculator. It's important to know how to use the tools you have, like your calculator.
Why do I feel like you're looking at me?
Oh no. I'm saying it to anybody that's listening, Vicki. By the way, Vicki. Oh.
Yeah, I know.
No. It's not just, it's, a lot of people don't know how to use the calculator. And we let you use one in class, so I try to show you how to do it. All right. So looking back, just so you may need to use that on one of these problems. Here's this. Don't forget to do the back page. It's here. This you do by the same thing. You want to graph y equals 2 to the x and do a transformation. And I'm not going to grade on whether you drew it or not, but most likely you'll get it right if you do these kind of drawings. Okay? So that's shifting. Reminder about shifting. All right. And then the last page of the notes. Here, we're almost done. The number e is defined as a number that is the expression 1 plus 1 over n to the n power. All that to the n power approaches as n goes to infinity. So that here's in calculus we do this with the limit notation as limit as n goes to infinity of 1 plus 1 over n, and there's a typo here. There should be an n up here. The limit as n goes to infinity of 1 plus 1 over n, all raised to the n power, equals e. The irrational number e is approximately 2.718, and it's called the natural base. The function f of x equals e to the x is called the natural exponential function. It's an exponential function because it has x in the exponent. It's a natural exponential because it's got e as a base. Okay, so we graph y equals e to the x. We could use our calculator for that. we're going to pick convenient values, or we could have just, we'll just do it like that. 0, 1, 2. And that's about all this graph will show. So we plug in -2 for x, we're finding e to the -2, 1 over e squared, or you can just type that in your calculator, e caret -2. That's what we're going to do. Calculator. Bring the calculator up. Second quit to get out of that. Second ln key is the e to the something. So ln, down here, right next to the 4, is e to the x. So you do second ln key, you get e to the x. If you want to raise e to an exponent, it sets it up for you, puts a caret, and puts a parenthesis. And then you want -2. Did everybody find that on your calculator? And since I'm graphing this, I'm going to just put 1 decimal place. This is a crude graph. I'm not going to be able to show more than 1. And then we can just keep doing that. Or we also have a second e. The divided by sign is also e, but it's not raising it to something. So we got e to the -1 is 1 over e. So you either do e to the -1. This is more work though, but or you do 1 divided by second e. You just want to use the second divided by sign is e. However you do it, this is 0.4 approximately. And e to the 0, anything to the 0 power is 1. And e to the 1, so you can just, that's just e. You can push second divided by, get the e and hit enter, and you get e. So that's about 2.7. And e squared, we put that in the calculator, so second natural log is e to the second power to 7.4. So here it is, -2 and 0.1, -1 is 0.4, 0 and 1, 1 and 2.7, 2 and 7.4, and it has a horizontal asymptote at y equals 0. That's the graph of y equals e to the x. We could have just got our 3 common points, this one, and this one. But I kind of like to get this one, just graph it more. You don't really need that one. All right, so that is the function e. Now, where in the world do we ever use this? Does anybody know anything about money and compounding interest? We use exponential functions when we're compounding interest. So if we've got an account balance, the balance A with the principal P, annual interest rate R in decimal form is given for n compounding periods per year. Our balance is going to be the principal times 1 plus the rate divided by n, all raised to the n times t, times time. And time is in years here. And we have for continuous compounding, A is principal times P to the rate times time. So there's an E function there. It's used anytime we have exponential growth, and we're going to see rabbits and I'll pass the, so, all right. I know you're tired, and let's just do 3-2 next time. Any questions?